All right, day 3, which is actually our second day, but we combined day 1 and 2 together. So this is technically day 3 of chapter 6. So we're going to work with some more separation of variables and specifically working with exponential growth and decay, which we touched on in math analysis in our exponentials and logarithms unit. All right, so separation of variables just literally means you separate your variables. Y is on one side, X is on the other. So dy goes with the Y's, dx goes with the X. Some steps to solving your differential equation. If they give you the differential equation as y prime, you'll want to rewrite it as dy dx so that you can then put your y's with your y, or your dy with your y's and your x with your dx. Rewrite each equation so that each variable occurs only on one side. Take the integral of both sides, and c is only needed on one side. Usually we put it on the right side. And then isolate the constant if needed. It is not always needed for you to say c equals something. Sometimes it's more appropriate for it to say y equals something. We're going to practice on the first one, making it say c equals. But isolate if needed. All right, number 1, solve the differential equation y prime equals, well, cut that text box off, didn't I? Equals 2x over y. So first step is we're going to replace y prime with dy dx. And then we want y's on one side, x's on the other. So it says divided by y, so we'll multiply it to the other side. We're going to have y dy, multiply dx over to the other side. 2x dx. So after you separate the variables, to be able to solve, that just means you're going to take the antiderivative. So we need to add the integral in. And then on this one, you can technically put the integral in between the 2 and the x because the 2 is a constant. It can come up front. And then we just do our rules. So we've got the antiderivative of y would be 1/2 y squared. On the other side, the antiderivative of x would be x squared over 2, or 1/2 x squared. But then what happens to the 2 that's in front? It cancels out, so we're left with x squared, and you only need to put the constant of integration on one side. So we can multiply everything by 2 to get rid of the dividing by 2. So if you multiply everything by 2, you would have y squared equals 2x squared, and then technically you would have plus 2c, but what is 2 times a constant? An even bigger constant, still a constant, so you can just leave it as c. And then if you were going to get y by itself, what would you do here? You would square root, and how many answers would it produce? It would produce 2 answers. But we're going to practice getting c by itself for if you need to find the specific solution for c. So to get c by itself, all you have to do is what? Subtract 2x squared. So you'd have c equals y squared minus 2x squared. You only have to do that if it wants you to find the value of c.
If we didn't multiply by 2 and stuff, there's 1/2 y squared minus x squared.
It's just not, they prefer it to not have the
No fraction.
Mm-hmm. But I mean, it's not wrong, but you need to be able to know how to get rid of it to eliminate the fractions, which I know you know how. But all right, so that's how you solve for c. Now we're going to check using implicit differentiation. So we're going to have c equals y squared minus 2x squared. Oh, I'm on a fat marker. Hang on. So implicit differentiation, we're taking the derivative, but anytime we take the derivative of y, we have to take it with respect to x. So we have to put dy dx or y prime. Okay, so this is back a few chapters. So what should we end up with at the end when we differentiate? What we started with. So what's the derivative of c? A derivative of a constant is 0. Equals the derivative of y squared to y dy dx. Then we would have minus 2x squared, the derivative of that, you bring your power down, so you'd have 2 times 2, which is 4, so minus 4x. And then because it's already with respect to x, you don't put dy dx. It's just normal differentiation. All right, so then we want to solve for dy dx. So we would add 4x to the other side. And then what? Divide by 2y. So we'd have 4x over 2y equals dy dx. And then what happens to the 4 and the 2? They cancel out. So we would have 2x over y. And then we can change dy dx to say y prime so that it matches the original. So if it ever asked you to check your solution using implicit differentiation, that's what they mean. You should be able to differentiate and get the original problem. Or if it just tickles your fancy to check all your problems, you can do that. That's totally up to you. All right, solve. Okay, solve means to anti-differentiate. We are at the first derivative. We have y prime equals x plus 3. We're just taking the antiderivative using separation of variables. So you want y's on one side, x's on the other. If they give you y prime, you write it as dy dx. So dy dx equals x plus 3. So the only y that we have is the dy, so it's going to stay over on the left. So we'll have dy equals x plus 3 dx. After you get your variables on one side, we add in Steve. So the antiderivative of dy is y. And then we're going to anti-differentiate x and 3. So add 1 to the power and divide by it. X squared over 2. And then the antiderivative of 3. 3x, don't forget, plus c. So if you needed to isolate c, you would move the terms to the other side, but it's not needed. That's our solved equation. All right, number 3. dy dx equals x squared y. So this time we do have a term with a y. How will we move the y to the dy? Divide. So we'll have dy over y equals x squared dx. Integrate. So remember, over here, you're really looking at the integral of 1 over y dy. What is the antiderivative of 1 over y? Natural log of the absolute value of y. And then the antiderivative of x squared, add 1 to the power and divide. Don't forget, plus c. All right, so this technically is not solved because it doesn't say y equals, it says the natural log of the absolute value. So to get rid of the natural log, we are going to exponentiate. So we'll have e to the natural log of the absolute value of y equals e to the x cubed over 3 plus c. That whole thing goes upstairs. So we talked about how the absolute value, over a week ago, how the absolute value produces the positive and the negative. Since we're working with exponentials, and exponentials aren't supposed to be negative, we can just kind of eliminate the positive and negative scenario, and we can just assume that we've got a positive value. If it ends up being negative, that will work out with our particular solution that we have. So, long story short, we're just going to have y equals, because the point of exponentiating is to get rid of your natural log. So we'll have y equals. And then upstairs, notice that you have e to the x cubed over 3 plus c. This is going to use that rule, that old school rule. If you have a to the m plus n, it can become a to the m times a to the n, because our rule with exponents was you can keep your base and do what with the exponents? add them, but we're reversing that. They're being added, and so we're going to actually split it into having two terms. So instead of e all raised to the x cubed over 3 plus c, we're going to have e to the x cubed over 3 times e to the c. What do you guys know about e? It's a constant, 2.7 and a whole bunch of change that never ends. So e raised to a constant is just a bigger constant, right? Y equals e to the x cubed over 3 times big C. And then where do we usually write big C when we have an exponential? You see it at the end? Do you see a number at the end? Like if it said e to the x cubed over 3 times 2, where's the 2 usually? In front, yeah. So y equals c times e to the x cubed over 3. Bada bing, bada boom. Pretty cool. We're going to be using this skill a lot with the separating of the variables being added and then separating it into two bases with their exponents today. So number 4, dy dx equals y plus 3. So notice on this one, what do we not have? We don't have an x. So you need to treat the y plus 3 as a binomial. Don't just like subtract y over and leave the 3 hanging over. Y plus 3 is going to be a binomial. So some of you will want to see this probably in 2 steps, so it makes sense. If I were to move the dx, the dx to the other side, how would I move it? I'd multiply it, so it would look like dy equals y plus 3 times dx. And then what would I do with the y plus 3? I would divide that quantity to the other side. So it's really dy over y plus 3 equals dx. All right, we need to steve it up. So if it helps you to see it as 1 over the quantity y plus 3 dy, you can rewrite it like that. If not, you don't have to. But the antiderivative of 1 over y plus 3 would be natural log of the absolute value of y plus 3. And then the antiderivative of dx, x, don't forget, plus c. All right, so then from here, how do we get rid of the log? Exponentiate. All right, so they cancel on the left. That's the point of exponentiating. We can drop the absolute value ours, and we'll have y plus 3 equals e to the x plus c. Leave that 3 over there until we're done working with the right side. That way you don't kind of mix it in there where it's not supposed to be. All right, so from the e raised to the x plus c, this is where we're going to separate it into 2 bases. Y plus 3 equals e to the x times e to the c. E to the c just becomes big C, bigger C. So I'm going to go ahead and put it in front. Y plus 3 equals c times e to the x. And then we move the 3 over by subtracting. So y equals big C times e to the x minus 3 hanging off the end there. Bada bing, bada boom. Woohoo. Any questions so far? All right, write and solve the differential equation that models the verbal statement. The rate of change of P with respect to T. The rate of change of P with respect to T is proportional to 10 minus T. So when it says the rate of change, what do you guys think of? A derivative, right? And it says it's the rate of change of P with respect to T. So how would we write that? Do I say that again? dP over dt. So if they said the rate of change of m with respect to t, you'd say dm over dt. Okay, whatever variable they're saying, make sure you write it appropriately. And then it says it is proportional to. So a proportion is a fraction equal to a fraction, right? So dp dt is proportional to, so equals is proportional to 10 minus t, except we're going to add this bad boy in. K. K is called the proportionality. Let me spell this right. Proportionality constant. Constant with a K. So you remember it. Proportion, I know it's not really spelled with K, but proportionality constant. So on these verbal statements, make sure that you put K in there. And then we're going to, we wrote the differential equation. Now we have to solve the differential equation. So we need to make sure that we have the variables on the same side. Well, we're not working with X's and Y's this time. We're working with P's and T's. And then K is the constant like, do we have one with a constant? Yeah, we had a 2. Okay, so 2 is the constant in that problem. It stayed with the X's. K is going to stay on the right-hand side with the T's, which are the X's. All right, so we need to move dt to the other side. So we're going to have dp equals K times 10 minus t dt. And then we need to integrate. I put the integral in front of K because K is constant. Remember, your constants can go in front of the integral. All right, we need to be careful on this one because the variables are kind of switched around. So we're going to use u and du here. So we're going to let u equal 10 minus t, which means du would be what? -1 or just negative dt. You guys are used to writing u equals and then du equals, and then you're putting a dx, but it's not x for our variables this time, it's t. So we're going to put dt. Do we have everything accounted for here? We've got u is 10 minus t, but we need du to replace a negative dt. So we have to balance that out. So I'm going to put a negative k times the integral 10 minus t dt. Oops. No. Yeah? Did I miss one? There should be a negative inside. I didn't balance. I'm like, wait a minute, I'm missing one. There we go. I didn't put one in. I balanced, but I didn't put one in. There we go. I'm like, wait a minute, I'm not going to get one to replace here. All right, so now that negative and that dt will get replaced with du. All right, so the antiderivative of, oh, no, just kidding. We want to replace. Let me get my u's and my du's. Sorry, I'm still in spring break mode. Negative k times the integral of u du. There we go. All right, so now let's anti-differentiate. The antiderivative of dp, P, equals negative k times the antiderivative of u. Power rule it. U squared over 2 plus c. Now we back substitute in. U was 10 minus t, so if p equals negative k, I'm going to put it over 2 times 10 minus t squared plus c. And you can leave it there. In your book, if you're checking your answers, they will have it like foiled out and distributed. They will do 10 minus t times 10 minus t and have your 100 minus 20t plus t squared, and then they'll distribute the negative k over 2 to everything. But you're fine leaving it here. But if you want to check your answer in the back of the book, you would FOIL, distribute, collect your like terms. Okay? All right. Growth and decay. All right, so in many applications, your rate of change of a variable y is proportional to the value of y. If y is a function of time t, the proportion can be written as shown, dy dt equals ky. So k is your proportionality constant. Dy dt represents, let me choose a different color here. This is your rate of change of y. The rate of change of y with respect to time is proportional to the value of y. So obviously it's got your y over on the other side. So it's saying that it is proportional to y, and then you've got k, which is our proportionality constant. So we worked with the rate of change of p with respect to time. This is your rate of change of y with respect to time. And the general solution of this differential equation, so this is the first derivative, you're looking at it as a differential equation. The solution to it, the antiderivative, is the following theorem. So it says that if y is a differentiable function of t such that y is greater than 0 and that your first derivative is equal to k times y for some constant k, then its original equation is y equals c times e to the kt, which is an exponential model. So if you were to solve dy over dt equals k times y, you would get y equals c times e to the kt every single time. So we're going to prove that. We're going to solve, do I not have it on this page? I have it on your page, right? Ah, there it is. All right, so we're going to solve this, and our answer should be y equals c times e to the kt. So once you've proved this, anytime we're working with an exponential model, we don't have to set it up as the proportion and then solve it out if we don't need to. If we can just go directly to the exponential model, we're good. Sounds good. I hope you make it. All right, y is on the same side, so how do we get y over to the other side? Divide, and then we're going to multiply dt to the other side. So we're going to have dy over y, separate the variables, equals k dt. Steve it out. The antiderivative of 1 over y, natural log, absolute value of y, equals, and then the antiderivative of dt is t, but we've got the k, so we'll have kt. Don't forget plus c. To get rid of the natural log, we're going to exponentiate. So on the left side, we'll have y equals e to the kt plus c. And this is where we get to separate it into two bases. Y equals e to the kt times e to the c. E to the c just becomes big C. So we get y equals c times e to the kt. Bada bing, bada boom. Woo! What does this look like? What exponential model of growth does this look like? Do you guys see? You worked with it a little bit in Algebra 2. We worked with it in math analysis. Compound interest, PERT, P times E raised to the RT. R would be equivalent to your proportionality constant. Anywho. All right, let's work with it using an exponential growth model. The rate of change of y is proportional to y. When t equals 0, y equals 2. When t equals 2, y equals 4. What is the value of y when t equals 3? So we're going to use, I'm going to color code this, so this will match my work down here. This we will use for step 1. What would the ordered pair when t equals 0, y equals 2, that ordered pair would look like? 0, 2. We will use this portion for step 2. That ordered pair would be 2, 4. And then what is the value of y when t equals 3? That'll be for step 3. And the ordered pair, what is the value of y when t equals 3 would be 3, comma, y, question mark, whatever you want to call it. Our goal is to figure out what y is at the end. We're going to use part 1 to find c. We're going to use part 2 to find k, our proportionality constant, and then obviously part 3 would be to find that value of y. So the rate of change of y is proportional to y. So the rate of change of y is proportional to y says dy dt. That's the rate of change of y with respect to time is proportional to, so equals, what can you not, okay, you can't just say y, we got to have the proportionality constant, k times y. So if dy dt equals k times y, then we know by theorem 6.1 that its solution is y equals c times e to the kt. So step 1, we need to find c. Well, it's going to be pretty easy. When they give you a time of 0 with a corresponding y value, it's always going to end up being that corresponding y value, but they do not always give you the time at like the corresponding y value with the time of 0. So if you're still like, how do you know it's going to be 2? This is what it would look like. So we would use y equals c e to the kt. We plug in. Our y is 2 equals c times e raised to the k times 0. Well, what is any constant times 0? Careful, 0. E to the 0 is 1. Anything to the 0 power is 1. 1 times c is c. So 2 equals c. Because k times 0 is 0. E to the 0 is 1. 1 times c is c. So 2 is the value for c. But that only works when they give you the time is what? 0. All right, so step 2, we need to find k. So you're going to rewrite the equation with what we know. So we started with the general y equals c e to the kt. Now that we know c is 2, we plug in. So we're going to say y equals 2 e to the kt. And then we plug in the values from the second ordered pair. So we have a 4 for y. So 4 equals 2 times e to the k times 2. Divide the c over first. So we're going to divide by 2 to get 2 equals e to the 2k. And keep in mind, we're solving for k. We want to get k by itself. So what do we need to do to both sides? We're going to natural log both sides. So we're going to natural log the 2 equal to the natural log of e to the 2k. So instead of exponentiating, we're logging. Remember the natural log of e, you better recognize. The natural log of e is just 1. So you bring down the 2k. So the natural log of 2 equals 2k. To get k by itself, we would divide by 2. So we'll have k equals the natural log of 2 over 2. This is where we want to store the value in our calculator. So find your natural log key. So natural log of 2, close your parenthesis, divide it by 2, get that crazy decimal up on your screen. Oh, you guys will have to put a decimal in. Did your calculator still say natural log of 2 over 2? Put in the natural log of 2 divided by 2.0 or just 2 point. and you should get this decimal. We will write down on our paper 4 decimal spots, but you can't use 4 decimal spots. You have to use that whole stored value. So to store, find your STO key, click store, and then we have to choose the variable. Usually we choose K because that's what K is. You know, we just solve for K. So you have to hit your alpha key is what color? White. So you'll hit your alpha key and then find where K is. K is above what? Or below what? Above the store key. And then my K is, where is my K? A, B, C, D, E, F, G, H, I, J, K. There, oh, dang it, alpha, okay. Hey, all right, so now we're gonna write down 4 decimal spots. You can round or you can truncate. We can do 0.3466 or 0.3465, it doesn't matter. 0.34, you guys want to truncate or round? Okay, 0.3465. You will not use 0.3465. You will just use it as you work through the problem, but you won't actually use that. You'll use K when we calculate it. So step 3, we rewrite the equation with what we know now. So we know y equals 2e to the 0.3456t. 65, not 56. And then we substitute in the value we want to find on this one, which is y when t is 3. So y equals 2 times e raised to the 0.3456 times, dang it. 4, 5, 6 just sounds better, I guess. 6, 5 times 3. So our variable is alone on the left side. You're literally just typing this in your calculator, but you're not going to use 0.3456 or 65. You're going to use the letter K. Maybe if I can get back to my calculator. There we go. 2. Your base of E should be around your natural log key. You'll have to hit a second feature or something probably to get to it. And then alpha K times 3. I don't know why on some I have 4, some I have 3. Go ahead and do 4 decimal spots. Yes, for these word problems, go ahead and do 4. 5 point, I cleared off my screen with 6. Help me out.
6.
Wait, 5, 6, 5, 6, 8?
Yeah, 9.
That's
9?
8.
Do I hear an 8? Okay. Oh, shoot. All right, that's it. Bada bing, bada boom. Whether you believe it or not, or remember it or not, we did do this in our math analysis chapter towards the very end of our exponentials. Storing for K. All right, so some radioactive decay problems. So radioactive decay is measured in terms of half-life. Half-life is the number of years required for half of your atoms in a sample, or it should say the number, most of the time it's years, but it does not have to be years. It's the amount of time, really, required for half of your atoms in a sample of radioactive material to decay. So here are some different half-lives. Pretty crazy. Suppose that 10 grams of the plutonium isotope Pu-239 with a half-life of 24,100 years, holy moly, was released in the Chernobyl nuclear accident. How long will it take for the 10 grams to decay to 1 gram? Long time. It doesn't matter.
We'll all be dead.
All right, so 10 grams is probably important. 10 grams would have been released at the initial starting time. So that's technically your first ordered pair. We know when t equals 0 that y equals 10. So we've got the ordered pairs here. Ooh, what was my first color last time? Tell me it was blue. Tell me it was blue. It was blue. Good, I wanted to keep that up. All right, with a half-life of 24,100 years. So 24,100 years is an amount of time. So we know if t equals 24,100 years, then its corresponding y value would be half the original amount. 5. Crazy. So 24,100,
How else was I gonna know that years is a unit of time?
I don't know. It's
They
kind of
don't
crazy.
teach this in like other.
They don't. Years, time. It's crazy. I mean, my daughter is still confused by units of time. She'll say, like, remember last year when I blah, 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 and she means yesterday, or remember last week? That was an hour ago. Whatever. Okay. She's only 7. But she knows that 30 and 30 makes 60, and 60 is in an hour. Yeah. Oh, red. All right, third color is red. All right, so we want to know how long will it take for the 10 grams to decay to 1 gram. So how long, they're asking you to find T. So the third color would be T is question mark, and then Y would be 1. So we're going to have question mark, comma, 1. Do what?
You can just keep like half of them.
Yeah, I mean, I don't think you can have 10 into 1 with a whole number.
It'd be close.
It was 5, it was 2.5, and it was like whatever half 2.5 is. That's pretty close to 1. That's pretty close to 1.
All right, so we have radioactive decay is exponential decay. So we're going to use the form y equals c e to the kt. You guys are goobers. So y is going to be 10 equals c e to the k times 0. Hey, k times 0 is 0, e to the 0 is 1, 1 times c is c equals 10. But this only happens when they give you the initial time of 0 with its corresponding y value. So step 2, we're going to find k, rewrite the equation with your new value. So we have y equals 10 times e to the k. Glad you made it. KT. So next set of ordered pairs we're plugging in is going to say 5 equals 10 times e to the k times 24,100. Good stuff. Divide by 10. 5 divided by 10 is 1/2. What? Crazy. I'm going to put it as a decimal so that when we log it and type it into the calculator, we don't have to type in the fraction 1/2. We can just put 0.5. If you want to write 1/2, whatever. So 0.5 equals e to the 24,100 k. Next step would be to log both sides, natural log both sides. So we get the natural log of 1/2 equals 24,100 times k. The exact answer for k would be the natural log of 1/2 all over 24,100. Go ahead and type that in. And we're not going to write down 4 decimals. We're just going to write down everything we see on the screen there, because it's a bunch of zeros first. Negative 0.0000, isn't there 4 zeros?
Yeah.
And then I wrote down 2876 on my paper. Is that what you guys have? No? 29?
Yeah.
What? Okay, I'll use whatever you have. 2 what? Just 29?
Yeah.
That's all it showed you? Okay. All right, go ahead and store that value, but store it when you store it to K, it will get rid of that old number, and now K will be this negative value. And it should make sense that your proportionality constant is a negative this time because this is exponential decay. Your amount should be decreasing. If you're growing, then your K should be positive. So get that stored in your calculator, and then step 3, we're going to rewrite y equals 10 e to the negative 0.1234029 times t. So this time you're not putting in 1 for t. 1 is the y value. So you don't just get to type it in your calculator. We have to actually solve it out. So 1 equals 10 times e raised to the negative 0.000029t. So our goal is to get t by itself. First thing we need to do is what? Divide by 10. So you can put 0.1, you can put 1/10. What do you want to put? 0.1. Just don't lose the decimal spot. So 1 divided by 10 is 0.1. 0.1 equals e to the negative 0.000029t. Natural log both sides. We get the natural log of 1/10 equals negative 0.000029t. Divided over, so we have t equals the natural log of 0.1 divided by that super small negative, which is k. So in your calculator, K-A-L-C, calculator. Okay. Divide that out. A whole bunch of years. Like Caleb said, we'll all be dead, so it doesn't matter. Hey. All right, 80,000 what? I wrote down 80,059. I'm so 50, so almost 59. So 80,058.5 years. Wowza. Woo!
That's a long time.
That is a long time. It's a very long time.
That's it's gonna take a couple minutes. All right. I'll go like watch Netflix or something.
All right. So we talked about how it's easy to solve for C when they give you the time at 0 and then its corresponding Y value. So this example is when they don't do that. So suppose an experimental population of fruit flies increases according to the law of exponential growth. So that's your clue, since it's increasing according to the law of exponential growth, that y equals c e to the kt. There were 100 flies after the second day of the experiment, and then 300 flies after the fourth day. Approximately how many flies were in the original sample? So first ordered pair would be what, comma, what? After 2 days, 100 flies, right? All right. Second ordered pair, after 4 days, there are 300. And then it wants us to figure out how many flies were in the original sample. So what's your time for the original sample? 0, comma, question mark, or comma, y. All right, so it says that it increases according to exponential growth. So we know that y equals c e to the kt. We know that that equation will fit. And so we're going to plug in the first ordered pair. We'll have 100 equals c times e to the k times 2. And so e to the k times 2 is like saying e to the 2k. we're going to isolate C. So we're going to divide by e to the 2k to the other side, and we'll have C equals 100 over e to the 2k. We're going to pause here and come back to this in just a second. Step 2, we're going to do the same exact thing with this ordered pair, but we're not going to isolate the C. So we're going to have 300 equals C times e to the 4k. And we know that this C equals what? 100 over e to the 2k times e to the 4k. So this is like having e to the 4k over 1 if you wanted to look at it like that. E to the 2k on bottom, e to the 4k on top. You've got the same base of e. Your exponents are 4k and 2k. What do you do with your exponents? You subtract them. So 4k minus 2k just leaves you with 2k where? On top. So we have 300 equals 100 times e to the 2k. Before we log it, divide by 100. So 300 divided by 100 would just give us 3 equals e to the 2k. Now we natural log it. Natural log of e is 1. So we get the 2k, divide, and we get k equals the natural log of 3 over 2. So make sure that when you type this in, you always close the parenthesis after the natural log of 3. Otherwise, it would be doing the natural log of 3 halves instead of the natural log of 3 divided by 2. I wrote down 0.5493. Tell me if that's what you guys have.
Yeah.
Go ahead and store that value. I know sometimes you guys will not store values and you'll just press your luck with it being a correct answer without using a stored value. Those of you who, usually it is, but those of you who are taking the AP exam, make sure that you are using stored values for sure. All right, so you stored that, part 3. Wants us to figure out approximately how many flies were there in the original sample. So there's a shortcut. Who remembers when they give you like the original time or the initial time of 0 with the initial amount? Like 0, let me flip back to one that did. Did I go too far? Where's one that gave it? 0, 10. Initial time of 0, initial amount of 10. What was C? 10. Where was the other? I thought we had one with a 2 here. Did I skip a slide? Oh, it was this guy. Initial time of 0 with an initial amount of 2. That corresponded to the C value. So yeah, we just plug in K to C. Like, don't rewrite the equation. Don't try to like resolve for something that you don't need to. We know C is 100 over e to the 2k. So we put in 100 over e to the 2 times whatever that was, 0.5493, but use that stored amount. Oh my gosh, I can't write. Go ahead and just round to a whole number appropriately. I have 33 written down. 33, don't write years. Bada bing, bada boom. Cool stuff. Woo. All right, 9:16. Welcome back.